Here are 3 isotopes of an element, C12, C13, and C14. There are 2 ways that I could identify which element this is, either by the element symbol, which is C, or by the proton number, atomic number, which is 6. Element C, atomic number 6, is going to be carbon. Here are 3 isotopes of an element, C12, C13, and C14. The number 6 refers to, you can see that they are all the same, and my element symbol is the same, which means that this is the thing that does not change when I am dealing with the same element. So that is going to be my number of protons, otherwise known as the atomic number. Here are 3 isotopes of an element, C12, C13, and C14. The numbers 12, 13, and 14 refer to, we have the same element symbol throughout, same atomic number throughout. These are the only things that are changing. The things that change with different isotopes is going to be the atomic mass. Here are 3 isotopes of an element, C12, C13, C14. What is the total number of protons and neutrons in the first isotope? Protons are the things that are going to stay the same. I can see that 6 is the thing that is repeating. So my number of protons is going to be that 6. And in the first isotope, my mass number is 12, and my number of neutrons is going to be my mass minus my protons. My mass is 12 minus my number of protons, which was 6, gives me 6 neutrons for that first isotope. Here are 3 isotopes of an element, C12, C13, C14. What is the total number of protons and neutrons in the second isotope? The number of protons is the thing that's going to stay the same. That is that number 6. So I'm going to have 6 protons. And my number of neutrons is going to be my mass minus my protons. My mass for the second isotope is 13, minus my number of protons is 6. So 13 minus 6 gives me 7. So there are 7 neutrons in that isotope. Here are 3 isotopes of an element, C12, C13, C14. What is the total number of protons and neutrons for the third isotope? My number of protons is the thing that does not change. That is going to be 6, so I have 6 protons. And my number of neutrons is going to be my mass minus my protons. My mass for my third isotope is 14, minus my number of protons, which was 6. So 14 minus 6 gives me 8. So I have 8 neutrons in that third isotope. For the isotope potassium-37, I need the atomic number. The atomic number is going to be based off of the number of protons, and it's going to be for potassium. Potassium is atomic symbol K. Its atomic number is 19. my number of protons is the same as my number of protons. My mass number is stated in the isotope notation. So potassium 37 has a mass of 37. My number of neutrons is going to be my mass minus my protons. So my mass was 37 minus 19. Gives me 18. And my number of electrons, I can assume that my number of electrons is going to be my same as my number of protons unless there is a charge stated. There is no charge stated. So I can say that it's the same as my number of protons, so 19. Oxygen 17, my atomic number is going to be 8. Since this is oxygen, my atomic number and my number of protons is the same, so I can go ahead and repeat that. My mass number is going to be the thing that is stated in the isotope notation, so oxygen 17 has a mass of 17. My number of neutrons is going to be my mass minus my protons, so I will have 17 minus 8. Gives me 9. And my number of electrons is assumed to be the exact same as my number of protons unless there is a charge stated. There is no charge stated, so that means it's going to be the same as my number of protons. So my number of electrons is 8. Uranium-235. Uranium is atomic symbol U, and its atomic number is 92. My number of protons is the same as my atomic number. My mass number is stated in the isotope notation. So uranium-235, the 235 is my mass number. My number of neutrons is going to be mass minus protons. So 235 minus 92. Gives me 143. And my number of electrons is going to be assumed to be the same as my number of protons unless there is a charge stated. There is no charge stated, so I can say that my number of electrons is also 92. Naturally occurring europium consists of 2 isotopes. I have a mass of 151 and 153. Europium-151 has an abundance of 48.03%. Europium-153 has an abundance of 51.97%. What is the atomic mass of europium? So europium-151 has an abundance of 48.03%. In decimal form, I'm going to move it over twice, so 0.4803. Europium-153 has an abundance of 51.97%. In decimal form, moving the decimal over twice, 0.5197. So 151 times 0.4803 gives me 72.5253. And 153 times 0.5197 gives me 79.5141. I'll add those two numbers together. and that gives me 152.0394. I'm asked to answer with 4 decimal places, so I don't need to round, but just to check to make sure that my number is reasonable, it should be between my lowest and highest isotope number, so it should be between 151 and 153. It is. And then if I was to find europium, it should be approximately around there. Looks like the europium that they were dealing with on the periodic table is a different isotope calculation, but that is okay. We have approximately 152, which is between my 151 and 153. Strontium consists of 4 isotopes with masses of 84 with an abundance of 0.50%, 86 with an abundance of 9.9%, 87 with an abundance of 7%, and 88 with an abundance of 82.6%. Calculate the atomic mass of strontium. So strontium 84 has an abundance of 0.50%. Moving the decimal over twice, that would be 0.005. Strontium 86 has an abundance of 9.9%. Moving the decimal over twice would be 0.099. Strontium 87 has an abundance of 7%. Moving the decimal over twice would give me 0.07. And then finally, strontium 88 has an abundance of 82.6%. Moving the decimal over twice would give me 0.826. And then I can plug those into the calculator. So 0.005 times 84 gives me 0.42. 86 times 0.099 gives me 8.514. 87 times 0.07 gives me 6.09. And then 88 times 0.826 gives me 72.688. Gonna add all of those numbers together. Gives me 87.712. Checking to make sure that this is reasonable. It should be between my highest and lowest isotope count. My highest is 88, my lowest is 84, 87 is between that. And so I need to answer with 3 decimals, so no rounding is necessary. So 87.712 would be my final boxed answer. Titanium has 5 common isotopes. Titanium 46 at 8%, titanium 47 at 7.8%, titanium 48 at 73.4%, titanium 49 at 5.5%, titanium 50 at 5.3%. Then I asked, what is the average atomic mass of titanium? So titanium 46 times 8%, so 8%, or moving the decimal over twice, 0.08. Titanium 47 times 7.8%, moving decimal over twice, 0.078. Titanium 48 times 73.4%, moving the decimal over twice, 0.734. Titanium 49 is 5.5% or 0.055. And then finally we have titanium 50 at 5.3% or 0.053. You can plug those into the calculator. So 46 times 0.08 gives me 3.68. 47 times 0.078 gives me 3.666. 48 times 0.734 gives me 35.232. 49 times 0.055 gives me 2.695. And finally, 50 times 0.053 gives me 2.65. I will add all of these together. And that gives me a mass of 47.923. Checking to make sure that this makes sense, this should be between my highest and lowest isotope. My highest is 50, my lowest is 46. 47.9 is definitely in the middle there. And then I need to answer with 3 decimals. This already has 3 decimals, so this is my final boxed answer. Calculate the atomic mass of copper if copper 63 is 69.17% abundant and copper 65 is 30.83% abundant. So copper 63 times 69.17%, moving the decimal over twice, is 0.6917. And copper 65 is at 30.83%. Moving the decimal over twice would be 0.3083. Plugging that into the calculator. So 63 times 0.6917 gives me 43.5771. And 65 times 0.3083 gives me 20.0395. Adding these two together gives me 63.6166. Making sure that this makes sense, this should be between these two numbers. It is. And it should be closer to the number that I have a greater abundance of. I have a greater abundance of 63, so it should be closer to 63 than to 65. It is. I'm asked for 4 decimals. This has 4 decimals, so this would be my final boxed answer. Boron exists in 2 isotopes, boron 10 and boron 11. Based on the atomic mass, which isotope should be more abundant? So I'm going to actually check on the periodic table. I see that the atomic mass for boron is 10.812, which means that I am closer to 11 than to 10. So I'm going to predict that boron 11 is going to be more abundant since I am closer to that number. Lithium 6 is 4% abundant. Lithium 7 is 96% abundant. What is the average mass of lithium? So lithium 6, we have 4% abundance. Moving the decimal over twice would be 0.04. And then lithium 7, we have 96% abundance. Moving the decimal over twice would be 0.96. So 6 times 0.04 gives me 0.24. And then 7 times 0.96 gives me 6.72. Adding these together gives me 6.96. And just checking, this should be between these two numbers. It is between 6 and 7, and 7 was substantially more abundant, so it should be closer to 7, and it is. It asked me for 2 decimals. This has 2 decimals, so this would be my final boxed answer. Iodine is 80% abundant at iodine 127, 17% abundant at iodine 126, and 3% abundant at iodine 128. Calculate the average atomic mass for iodine. So iodine 127, we have 80% abundance. Moving the decimal over twice, it'll be 0.8. Iodine 126 has a 17% abundance. Moving the decimal over twice would be 0.17. And then iodine 128 has a 3% abundance. Moving the decimal over twice, 0.03. So 127 times 0.8 gives me 101.6. 126 times 0.17 gives me 21.42, and then 128 times 0.03 gives me 3.84. Adding these all together gives me 126.86. Checking to make sure that that makes sense. This number should be between all of these. My lowest isotope mass was 126. My highest was 128. This is in between those, so that seems reasonable. I'm asked to answer with 2 decimals, and this is 2 decimals, so this would be my final boxed answer. The natural abundance for boron isotopes, we have boron 10 at 19.9%, and at boron 11 we have 80.1%. Calculate boron's atomic mass. So boron 10, I have an abundance of 19.9%. Moving the decimal over twice would be 0.199. And boron 11 at 80.1%. Moving the decimal over twice would be 0.801. Going ahead and calculating that. So 10 times 0.199 gives me 1.99, and then 11 times 0.801 gives me 8.811. Adding those together gives me 10.801. My number should be between these two numbers. It is. And it should be closer to the abundance that I had more of. I have more boron 11. This is closer to the number 11. This is reasonable. I'm asked to answer with 3 decimals. This has 3 decimals, so this would go ahead and be my final boxed answer. Hydrogen 1 has an abundance of 99%. Hydrogen 2 has an abundance of 0.8%. Hydrogen 3 has an abundance of 0.2%. Calculate the average atomic mass using 4 decimals. So hydrogen 1 at 99%, moving the decimal over twice would be 0.99. Hydrogen 2 at 0.8% would give me 0.008 after I move the decimal over twice, and hydrogen 3 at 0.2% After I move the decimal over twice would give me 0.002. So 1 times 0.99 gives me 0.99. 2 times 0.008 gives me 0.016. And then 3 times 0.002 gives me 0.006. Adding all of those up gives me 1.012. Checking to make sure that this was reasonable. It should be between my lowest and highest isotope amount. It is. And we have a very heavily weighted isotope at hydrogen 1, so it should be very close to hydrogen 1. It is. I'm asked for 4 decimals. So that means I need to add a 0 at the end there. And that would be my final boxed answer. Rubidium is a soft, silvery white metal that has 2 common isotopes, rubidium-85 and rubidium-87. If the abundance of rubidium-85 is 80.2% and the abundance of rubidium-87 is 19.8%, what is the average atomic mass for rubidium? So rubidium-85, we have an abundance amount of 80.2%. Moving the decimal over twice would be 0.802. And rubidium-87, we have an abundance amount of 19.8%. Moving the decimal over twice would be 0.198. So 85 times 0.802 gives me 68.17. And 87 times 0.198 gives me 17.226. Adding these two numbers together, we get 85.396. Checking to make sure that this makes sense. My final answer should be between my lowest and highest isotope mass amount. It is. And I have a higher abundance of rubidium-85 than rubidium-87, so it should be closer to 85 than to 87. It is, so this seems reasonable. I'm asked for 3 decimal places. This already has it, so I'm going to go ahead and say that that is my final boxed answer. What is the atomic mass of hafnium? If out of every 100 atoms, 5 of them have a mass of 176, 19 have a mass of 177, 27 have a mass of 178, and 14 have a mass of 179, and finally 35 have a mass of 180. It says out of every 100 atoms, you must remember that percentages are out of 100 anyway. So for hafnium, 176, if I have 5 out of 100, that is 5%, or 0.05. For hafnium 177, I have 19%, 19 out of 100, or 0.19. For hafnium 178, I have 27 out of 100, or 27%, or 0.27. For hafnium 179, I have 14 out of 100, or 14%, or 0.14. And then finally for hafnium 180, I have 35 out of 100, or 35%, otherwise known as 0.35. Okay, 176 times 0.05 gives me 8.8. 177 times 0.19 gives me 33.63. 178 times 0.27 gives me 48.06. 179 times 0.14 gives me 25.06. And then 180 times 0.35 gives me 63. Adding all of these up, gives me 178.55. Making sure that that is reasonable, it should be between my lowest and highest isotope amount. It is. I'm asked to answer with 2 decimal places. This already has 2 decimal places, so this would be my final boxed answer.